Welcome to the Lecture 7, wrapping up our Unit 1. In this last lecture set for our Mechanics 1 unit, covering motion and forces, we have a grab bag of a couple different things. In the first half, you will see demonstrations of one each of the multiple choice and of the essay timed assessment, along with some explanation of logistical details for the assessment. After watching these demonstrations, when you feel ready, try your own attempt at these assessments. Do your best, and we'll be talking about your assessment attempt, and you will have a chance to add explanations and talk about what you learned at our one-on-one meeting. So don't worry too much about the assessment itself. In the second half of the videos, we have a couple optional lectures, going a little bit further into Newton's law of universal gravitation and its connection to astronomy and our understanding of our own neighborhood. The lecture videos I am using here are borrowed, again, from Physics 4a, but they cover mostly conceptual stuff, so I think most of the content will make sense as they are presented here. There are a couple places talking about Kepler's laws, which we won't cover, and angular momentum, which we will cover later. But I think the illustration using the SpaceEngine simulation makes sense without these extra topics. Do please reach out to me with any questions. This is it. In the next lecture set, we will dive straight into our discussion of energy, the first of the conserved quantities we will introduce and use. Oh, and before I forget, all the videos in this lecture set were recorded before the shift in textbook chapter and section numbers. So when I am doing demonstration of multiple choice timed assessment for chapters 1 and 2, that corresponds to our chapters 0 and 1. And when I am doing demonstration of essay timed assessment for chapter 3, I am demonstrating a question from our chapter 2, the chapter on forces. Your version of assessment will have these shifts reflected. Okay, so I'm gonna get started. So with this timed assessment, the system will warn you as you're trying to start, because there's a time limit. Once you click on start, then the time doesn't stop for any reason. You have 10. So once I start, I have until 6:18 to finish the assessment. So with that in mind, I'm gonna start. And there's a timer here. Yeah, the timer tells me how much time I have. And these rules, you had access to it before you started, so you shouldn't be wasting a lot of time reading through this. So let me just work through. You get 10 questions, come in order, and once you work your way through down to the bottom, that's where you submit. And as you work through this set, it'll save your work. You see how it says progress saved? So somehow if you get disconnected, somehow you are not able to click the submitted end button at the end, there will be still some saved work that can be used in some way. So I'll just work through. Okay, suppose you're holding a meter stick, ruler that is meter long, marked on one side in centimeters. Approximately how many marks do you see? Oh, inch side. Now I happen to know that inches are about 2.4, 2.5 centimeter each. Or I guess better yet, I know in 1 yard there are 3 feet, and in 1 foot there are 12 inches. So 1 yard has a 36 inches, and 1 yard is about a meter. So it should be 30 marks. Choose the choice which most correctly completes the sentence. In order for the laws of classical physics to apply, it is necessary to have situations. Classical physics. Oh, it's the thing about the speed of light and some size scale, special relativity and quantum mechanics. So it must have speed much less than speed of light. And the size, that's not necessary. So I think that's the right choice. Question 3, answer for an object thrown straight up and falling down on Earth. Taking upward as positive, that seems natural. statement which most correctly describes this situation. Velocity is not zero on the way up. On the way up, it's positive. So I'm going to go to the next choice. Velocity is zero on the way down. It's negative. Velocity of this object is zero at the top. Its velocity changes the direction at the top. At the top, the acceleration due to gravity at the top. Something seems to be wrong here. There may be an issue with the question. Just trying to see. All right. So actually, I'm gonna do this, which is what I recommend. So if you see something weird in the question, do this. First, open message instructor window. Now, don't waste the time doing this because 10 minutes is very short. I've opened this, so I can do that after I'm done. But for now, I'm gonna do my best to answer this. So velocity of the object is zero at the top. That seems right so far. And there's some grammatical issue here. Okay, I'll let that be, but I'm gonna select this and then move on. And what I have as a reminder to myself is I'm gonna come back to this later and send me a message that something seems to be wrong. That's I think a good thing to demonstrate in this recorded session. For this question, let the right be positive, left to be negative. If a runner runs to right while slowing down, okay, runs to right, so velocity should be positive. Slowing down, which means the acceleration is in the leftward direction, so that should be negative. So velocity is positive, yeah, acceleration is negative. Okay, which of the following statements most incorrectly describes the properties of projectile motion? Okay, that's correct. Speed of projectile is slowest at the top of the motion. Seems reasonable, so probably correct. Projectile motion can be, yeah. This is one of those definition thing. If something is undergoing a projectile motion, then by definition, air resistance should be negligible. If it wasn't negligible, you shouldn't have called it a projectile motion. It doesn't make a lot of intuitive sense. It's just a definition thing. And I guess you can also do it by process of elimination. Consider a cannon that can fire if the initial speed of the means same. Oh, I think I've seen this example before, 45 degrees. Oh, wait. I need to read the question. It'll stay in the air for the longest possible length of time. It's not asking me when, at what angle it'll have the maximum range, which was what I was thinking of, but I need to answer what the question asks. So for that question, it needs to be 90 degrees. So that I'm firing it straight up, that'll maximize the amount of time in the air. Okay, for this question, let right be positive, left to be negative. Car moves to the left, okay, negative velocity while speeding up. Now, this is the tricky part because if it's speeding up while it's moving to the left, then acceleration is pointed to the left. So acceleration is also negative. So velocity and acceleration are both negative. Okay, seeing a traffic jam ahead, a motorist taps the brakes, slowing down at this speed for next 6 seconds. At the end of the time, what is the motorist speed? The initial speed was that. All right. I can do this in a calculator really without writing things down. So my initial speed was 34. The motorist is slowing down, so I'm gonna be subtracting a number. And the number I'm subtracting is the acceleration times the duration of time. 3 times 6. Hopefully you remember from your reading that change in velocity is acceleration times the duration of time. There are some calculation questions, not many. So, if you want to skip questions like this, fine. That might be a good time management. But chapter 2 is weird. It's one of the most mathematical chapter in the entire semester. Okay, consider a rock thrown directly upward at this speed. Use that. Ignore the air resistance. Okay. How long does it take for the rock to reach the highest point of the trajectory? Okay. This might be worth writing down. So this is one of those calculation questions. Maybe if you don't immediately know what to do, you might want to consider skipping. But here, what I'm remembering is the change in velocity is the acceleration times the duration of time. By the way, I'm watching my time here. 6:15, I have 3 minutes, and I'm looking 2 questions, 3 minutes. I have enough time, that's why I'm wasting my time here. So I'm looking for duration of time. So duration of time is equal to change in velocity divided by acceleration. So I'm looking at these numbers. My velocity is going to change from 35 meters per second to at the highest point, my velocity there is 0. It's something that I hope you remember from your reading. So my change of velocity is going to be 35 meters per second. My acceleration, the magnitude is 10 meter per second squared. So work this out, you get 3.5 seconds. Do I see? Yeah, well, it takes around 3.5 seconds to reach the highest point. Okay, I'm almost done and also almost out of time. Which of the following are generally correct features of a constant acceleration motion? Velocity is not constant acceleration. So if you have non-zero acceleration, that means velocity should be changing. In fact, the velocity is changing at constant rate. That's the feature of constant acceleration. So that's all my answers. So at this point, I can submit an end. It might be worthwhile. So I'm gonna do this. Oh yeah, 8 out of 10 answered. So I want to click on save progress. So I have 10 out of 10 answered. And I think I can show you what happens when your time runs out and somehow if you didn't get to click submit and end. So let me do that. I'm gonna go write this message to myself. The question choices sound ungrammatical, i.e. Um, here the velocity and like at the top yeah, ungrammatical. uh, is there something missing before at the top? I tried my best to select the correct answer. And when you send me a message like this, what this gives me an opportunity, what this lets me do is I will get the message and I'll take a look at it eventually. I'm not going to answer within your 10 minutes. In fact, I don't even recommend that you use any of your 10 minutes to do something like this. But it lets me look at the choice, look at the question, fix anything that's wrong, and make sure that no one's losing points unfairly. And so I'll take a look at that and fix that after the session. So I sent to that. Oh, yeah. And while I was doing that, wasting time, I ran out of time. And I think here the system automatically submitted it for me. And probably because the window was open. And yeah, I guess that's it. Um, I'm glad I got 100%. That's not as embarrassing as it was going to be if I didn't get 100%. And so my intent always was to hide the grade, but it doesn't work that way. The way LTI works, you will always see your recorded score. I've tried to hide this and I can't, so you're just gonna see it. And you can review work, but what it will never tell you is which questions you got right. So for example, if I got 80%, then I don't know which 2 questions I got wrong. And that is mainly to encourage you to study. Uh, Although I guess I'm not sure how. So, this is what you can do. You can always message instructor and ask me, hey, did I get this wrong? And hopefully you have some sense of which questions you got right for sure and which questions you are unsure of. Like this one, where there was something ungrammatical. So that's where you might message me and say, hey, I got 80% or something. And I think this might be one of the questions I missed. And so yeah. So with a multiple choice timed assessment, you do get 2 attempts. So if you get a score and you don't like it, then you can reattempt, and the system will keep the best score. So you don't once you get 100% or once you get 80%, then you don't have any danger of losing that position of 80%. I see a question in the chat. Let me just read it. Regarding the negative acceleration question, are there situations on the test where we need to keep an eye out for the terminology difference between acceleration and delta V? So delta V is also a vector. Um, so because the velocity is a vector, you can see that in one of the questions here, which is so I think the way I was going through it, I didn't really highlight it. So for this question, let the right be positive and left to be negative, and so so when we say velocity is positive, what we are really saying is the velocity vector is pointed pointed rightward. That is what we are saying. And now I guess if you are as this is one thing that I can imagine some people getting caught up, which I think was demonstrated in one of the questions here. Um, so I can imagine some people saying, oh, here the acceleration is positive because the car is speeding up. And this is where I've treated acceleration as a vector quantity. That's why I said the acceleration is negative, because all that I meant was acceleration is directed leftward. That's all I mean. And I don't think I have any questions that actually ask. Um, sorry, I'm trying to get rid of this. Okay. Um, um, I don't think I have any questions that directly asks about delta V as in change of velocity. If I did, you would treat delta V as as vector. Um, I think if I wanted you to treat it like speed going up or speed going down, I would actually use this phrase: speeding up or slowing down. One phrase that you would never see me use in this class is the phrase deceleration, because I think that's just hugely confusing. So I never use the word deceleration. I will always say speeding up or slowing down, and those always refer to the change of the speed, change in the magnitude of velocity. So I guess that would be scalar. Maybe that's what that's what the questioner meant. So okay, so having done all that, let me show you why watching this recorded video won't give you all the answers to the um, multiple choice timed assessment for chapters 1 and 2. And this is why I feel comfortable doing this on recording. Let me leave my student view so that I can go into my instructor view. And I was just testing things out and show you how this is set up. When I go to LTI home, go to questions, this is how the whole thing is set up with. So I use something called a question pool, and it has some structure to it, particularly for an assessment that has multiple chapters in it. I have it set up so that all the first 2 questions always are from chapter 1. And that's what this means, choosing 2 without replacement. And the system is choosing those 2 questions from a pool of 12 questions. So out of the pool of 12, you've seen 2. So for those 2 that you have seen, you have some idea of what the answers are, but there's still 10 that you haven't seen yet, and there's a good chance that the 2 questions you will get will come out of the 10 rather than the 2. The questions from chapter 2. So that's the remaining 8. And those remaining 8 are chosen out of a pool of 50 questions. And you have seen 8 of those 50 questions. So, when you take your assessment, there's a probably good chance that 2 or maybe even up to 3 questions that you will see are from the ones that you've seen me do. Now, even in those cases, I do want to warn you that this is a sophisticated system, which is I love about it. Some of the questions are dynamically generated, or some of the questions have multiple versions in one. So just because a question sounds similar, you shouldn't assume that it's exactly the same question, because the dynamically generated one is that I love the most, because I name it dynamically generated because it generates a number of choices that are just a lot. So which question was this? All quantities below as vectors and scalars, yeah. And the way this question is generated, I have a list of things that are vectors: displacement, the force, velocity, which you have seen. List of things that are scalars: distance, energy, speed, temperature. And there's this code here that puts these things together, and the statements are relatively unique. um, so in fact, the one that I sent the message about, it's one of those dynamically generated ones, and the bug that I had to find and fix are one of these things. So I'll do that off session, because and um, so so really the purpose of these assessments are to test your understanding. And so that's why I feel, and especially for multiple choice questions, I have a really rich set of questions. That's why I feel comfortable doing this at least once, and possibly even twice on recording, because in this recording I'm showing you basically how the process works without giving you a lot of answers that'll, I'm not giving away any answers to the questions. Really, the way to do well on these is to study, so that no matter what kind of questions you get, you can do well. Now, I can give you some level of assurance that you can really do well by studying your homework questions. So let me just pick a question at random here, like this one here. So, so this question here, when the question description says test bank version, and this is the sense in which it's a test bank version. It's derived from this question here, 205 H60. And oh, okay, it's gonna take a little bit of time for me to find this question, but let me just find it so that I can tell you, I can give you some level of confidence on what you should be studying for. So let me do this. So I picked this question at random, and this question says that it's derived from this particular question. All right, I'm gonna go to my open math, and I have to guess what set this comes from. That's the hardest thing. Uh, I think I'm gonna guess this set. That's what I'm gonna guess. And if I'm somehow wrong, I'll move on to the next set. I'm searching for that question number, 205 A60. Okay, not the right one. um, Maybe this one, I think. 205 A. Oh, there it is. Yeah. So that's the question that this question was supposedly derived from. So let me preview this. Oh, wait, did that? Okay, it did not replace that. Okay. So these are the two questions. So this was one of your homework questions. It says, choose a valid unit for acceleration, and when you were going through homework, you had a chance to think about it, work through it, and the ones that should have been the correct answers were these two. Now, on the test bank question, it asks, okay, which of the following is a valid unit for acceleration? And one of these two correct choices, this one, is the correct answer for your test bank question. And I can guarantee you, for close to 100% of your test bank questions, they have a matching homework question. So I'm not guaranteeing that every homework question will lead to a test bank question. What I'm guaranteeing you is that close to 100%, 95, 99% of your test bank questions, you can trace it back to a homework question. So if you have understood every homework question perfectly, then you can do every test bank question perfectly as well. So as you're studying and preparing for the timed assessment, what I would recommend is review your homework. That's your best resource for preparing for these timed assessments. Even the calculation questions, you should be able to find the homework version. So yeah, so take it once, and if you get 20%, then study, prepare, and then take it again when you feel ready. You get 2 attempts, and really the first attempt, it's intended that you might be using that as a practice, so, to get a sense of how well you are prepared. And if you do it and you get 100%, great. You can move on to the next one. But if you got something that you're not happy with, 50%, 70%, 30%. Different people have different, level of expectations. If your first attempt isn't what you're happy with, then I would really recommend, rather than just immediately retaking, to study and prepare before you retake. So this is the test student view, and I can do this without having done chapter 2 because I can skip around for this module. So this is the instruction. I would recommend that you read it carefully. And here's a bit of information that I think a lot of people might not have realized how much it tells you. The thing about the one open-ended question, I liken this to like a job interview question where the person asks you, so this would be the interview question. So tell me about yourself, or tell me about your educational and professional experience. It's an open-ended question, and you can almost guarantee that any job interview you go, you are going to get that question. And you have a question like that with every essay timed assessment. One question where you can, even before I ask it, you can kind of know what the substance of the question will be. Knowing that might help you prepare ahead of time. I think when I set the time limit at 20 minutes, I didn't presume that, but kind of preparing for it ahead of time might help you save more of this 20 minutes for the less predictable second question. So let me start this. So the open-ended question, the one question you see, it's going to be the same question that you get when you start. So for this open-ended question, really what I'm looking for is your unique answer. There isn't one right answer. It is in your own words. So do your best to summarize. I do have a word limit, so don't copy the entire textbooks into here. You can put the entire chapter in 200 words. You have to summarize. So this time, let me just give a genuine answer here. I'll give a genuine answer. So what my answer would be here is chapter 3 covers, don't know why these show up. Newton's 3 laws of motion. Oh, and Newton's law of universal gravitation. Newton's laws of motion. Um, Relates or it introduces the force concept and relates the force, a push or pull, or a pull, to the acceleration caused by the force. Newton's third law of motion in particular describes the, I don't know if I would call it surprising, or I'll say it this way. Newton's third law of motion, sometimes confusingly stated as for every action, there is an equal and opposing reaction. The saving part here is that I said it's confusingly, because this statement is not what I recommend. Describes how objects interact through force. Yeah, and I guess I'll say chapter also, the chapter also described several types of forces, such as normal force, friction force. I think I covered the spring. Did I cover spring force? Maybe, maybe not. I might be bringing that in from chapter 4. um, Normal force, friction force.
I feel like there should be, and gravitational force. Um, let's see what else. Gravitational force, which is an inverse square law of force. And I think this is a response that's on the low end side. Let me do a word count. Now, I don't do word count with every answers. I just do it with the ones that I feel are too long. Is there? I guess Notepad is too simple to have word count tool. Let me see if I can bring up stuff in Word without. Gonna, okay, I think that's fine. um, by the way, I guess unless you thought you wrote too much, yeah. So 87 words. So this is on the short end, but this is probably so if I read this, I would probably give full credit to this answer because I am summarizing in 200 or fewer words key points. Sometimes an answer can be too short and miss key points, but here I am describing all the most important things. Newton's all four laws that's covered in the chapter, and and I guess I forgot. Wait, do I need to talk about centripetal force? No, I don't think I really need to. Um, yeah, and chapter covers other things like microgravity, which appeared in one of your essay questions, essay assignments, and other things. But the intent here is not that it needs to be comprehensive; it's that it illustrates what you learned, what you consider to be highlights of the chapter, and yeah. So do your best there. So that's that open-ended question is one question you will always see for every chapter timed the essay timed assessment. For the chapter 2, you will see basically the same question that relates to chapter 2. Yeah. So now I have 14 minutes remaining for the remainder of the essay assessment. I got the question about the talking donkey, and I guess I'll read it out loud. Talking Donkey refuses to pull on a heavy cart, arguing with you that it's meaningless for him to pull it because for every action there is equal and opposite reaction. I literally didn't see this before I put that up there. According to Newton's third law, he is arguing that as he pulls on the cart action, there will be a reaction force on the cart opposite in direction. So the net force on the cart will be zero, meaning that the cart won't move according to Newton's second law, according to the talking donkey. You know that this talking donkey must be wrong because when you pull on a cart, it does move if you pull it hard enough. Clarify the donkey's misunderstanding of Newton's third law and correctly identify the reaction force to the donkey's action force. Donkey pulls on cart and the actual effect of this reaction force. By the way, when we used to do paper exam, this question used to ask for like a diagrams. On this online format, you can't really draw diagrams, so questions will seek more of a word description than a diagram. So I do, as you're reading the question, I do want you to be careful to note all the instructions because it says clarify the donkey's misunderstanding and it says correctly identify the reaction force pair. So I look for those things as I grade. So let me put an answer here. So the donkey's misunderstanding of Newton's third law. The donkey didn't fully grasp Newton's third law is a law of interaction. That is, it describes a pair of forces not on a single object, but instead two different or, or a pair of, of objects that are interacting with each other. it is true that the sum of the action force and the reaction force will be zero. But because the action force and the reaction force act on different bodies, the net force on an object due to a particular action force can be non-zero. The reaction force is on another object, uh, yeah, on another object, and Um, so that's my summary of Donkey's misunderstanding, part one, and correctly identify the reaction force pair. Um, the reaction force pair to donkey pulls on the cart. And I think here I deliberately described it in a way where um, people think of it. Did I? Maybe. I don't know. So, one thing about action reaction to make sure that you understand, it's not a cause and effect. So if you think a donkey pulls on the cart, that's the action, and the reaction is cart accelerates. You didn't understand Newton's third law correctly, because the action force and reaction force, they are not cause and effect. They occur simultaneously. One doesn't cause the other. There are two sides of one thing that happens all at once. So as the donkey pulls on the cart, the thing that happens is cart pulls back on the donkey. And in fact, because action reaction is not a cause effect relationship, you can actually reverse these two things, and it should still make some sense. Like if I said instead the action force is cart pulls on the donkey, because cart is around the donkey, so as donkey tries to move forward, the cart thing is going to just hold the donkey back, so cart pulls on the donkey as donkey tries to move forward. And the reaction force is donkey pulls on the cart, because the cart is pulling back on the donkey. The reaction is that donkey ends up pulling on the cart. Is another way to describe the same interaction. Um, and in fact, this is why the donkey finds that it's harder to move forward. Oh, yeah. Wait. I don't know if I want to do the bonus point question. You don't have to anyway. No, I kind of ignore it when I grade. That's why it's a bonus point, meaning it's not required. This is why the donkey finds that it's harder to move forward when the cart is attached to the donkey. So yeah, I think I have some time left. I have 8 minutes left, and yeah, I guess that's fine. So when you feel like you're done, you feel like you answered everything. So with the essay timed assessment, 20 minutes should be on a relatively long end. I think if you have studied, and if you don't need to look through your textbook as you're answering this, you should find that 20 minutes is plenty of time. I was almost tempted to pare this down to 10 minutes, but I think the speed at which I type isn't necessarily representative of the average speed at which people type. So I gave people more time than I would need to if I were the one typing. So I think 20 minutes for essay assessment will end up being enough time for most people. But if somehow you're finding that that's not the case, or if somehow you have difficulty typing quickly, maybe you are working on a mobile device, then do let me know so that we can work something out. Now, with essay timed assessment, I think, does it give you the score? It doesn't show you the score, which I'm glad, because if it were showing you the score, it would have told you that it's 0 out of 10, and that could have been very confusing. In fact, even though it might still, this is the vagaries of LTI. And I think because of LTI, there might still be a score here. Essay time. Oh, wait, I don't have anything here yet. Huh, so maybe it won't be sending me a score. Um, if it does, and if there's something that says 0 out of 10, yeah, okay, yeah. So you'll get notification, oh, your essay timed assessment is graded, and you got 0 out of 10. Ignore it, because it's just an automatic thing. And like it guarantees that 0 is a score I use only for blank answers. So even if your answers are super terrible, the minimum you would have gotten is 2 out of 10, 1 out of 5 for each. So this 0 is an indicator that it hasn't been graded yet. And here's another thing that'll tell you that it hasn't been graded yet, which is that when you view work, this is how you review your work. It's how you view feedback for your work. You will see no feedback at all. That's because I haven't graded it. And so I might talk about this more, but this is my grading process. Let me do it here. So I'm just gonna move this off the screen briefly so that I can navigate to the test students grade item and not show any. Well, I guess there's no one's graded here yet, but I don't want to show who's done this already or not. Okay, so this is the screen I see when I grade. This is the assessment attempt. I see all these detailed stuff, and I see this. All right, this seems short enough. I don't have to do word count. If I see something that's like 3-4 times this, then I'll start doing word count to see if it's way over 200, then I should start taking points off. And so full credit, and then here I'll read it, and if I mean, I just wrote it. Oh, let me compare it to the answer key. Did I? Oh, I think this answer key says this because I'm still thinking of the one version in the diagram. So, but it says actual reaction force is the force that the cart exerts on the donkey, which is why donkey van. Yeah. Do I? Why the answer key doesn't explain what donkey's misunderstanding is? I might have to rewrite this. Yeah. But I it's fine. I don't think it's relevant. So I'm giving you full credit. And because I think I don't want to bother with the score. So in the feedback, I will tell you the score on individual part. It worked. So when I save change here, it's going to take me to gradebook. So I'm going to do that off screen or off the shared screen. And oh wait, it didn't take me back. Okay. All right, I'm still here. Let me go into student view and show you what the feedback looks like. So this is one of those things where it's really hard to find the feedback, and this is how you'll find it. If you click on review work, you will see the assessment attempt, and you will see the feedback here. And sometimes I might give you a per question feedback. You will see below each question. Sometimes I'll do that if I need to comment extensively on a particular question. So when you see this, that's when you know, oh, it's been graded. So, yeah. And if I look at the gradebook, now you should see that. And so as I graded, Canvas will also send you a notification. Takes some time. Canvas will send you a notification. Oh, it's been graded, and now it's 10 out of 10, and that's when it's an actual score. So that's the demonstration of the timed assessment, and just so that you know what to look forward to. So these are due on Friday. I recommend that you get it done by then. And somehow, if you don't get to it, then late passes are enabled. So you can use late pass on these to get them done over the weekend. But if you are ready, take them before on the due date. And this is more of an item for me. I need to reach out to everyone to schedule individual one-on-one meetings. That's a follow-up meeting on this timed assessment. We'll go over what I see in your work. If your work looks great, then I might have some follow-up questions, go more in depth. If there are things that were wrong, then we might talk about that. But so this is the required meeting for this class. Your video has to be on, and I'll be checking your ID for this first meeting, and yeah. So, but you'll hear about this weekend. So I'll leave that there.
So I have talked about this before. These are, if you read the preface, then he would describe where it comes from. So this came from lower division introductory physics, introductory in the sense that these are the first physics classes that science and engineering majors take at Caltech. And he gave these lectures first three semesters, I think. That's what volume 1, 2, 3 divisions are. And guess, does it tell you the year? It was done in the 1960s, yeah. So that's where it comes from, and I think I've said this a couple times that you can't really use this as a textbook for a class because the orders are so unusual. You know, he's talking about conservation of energy long before even introducing kinematics. And so with that caveat, it is a classic. So if you ever major in physics, it's something that many of your physics professors would have read or at least heard about. And from my personal perspective, I think the first summer when I was in college, I spent the first few weeks of the summer just reading through the book and the volume one. And I remember just getting a really fresh perspective, understanding the laws of physics and the physics problem solving in ways um, that I didn't quite get from the textbook that we were using then. So this is a kind of supplemental thing because it gives that perspective. Now, one thing I do have to say is that it's from the 1960s. So to the extent that there have been progress in physics, fundamental physics, or engineering, that wouldn't be reflected in this book, especially in the fields of engineering. With the fundamental physics, there haven't been any new fundamental paradigm shifting discoveries in physics since about 1980s or so. That's when what we call standard model of particle physics was completed, and then since then there have been particles discovered. There have been discoveries, but none of the discoveries since then changed the paradigm of how we are organizing things. So to that extent, the encouraging thing here is that a lot of this is kind of up to date because it's the sort of thing that doesn't change. So, anyways, so I had a couple of sections picked out that I wanted to just read through. I think this was when I was teaching astronomy. There was story about Newton and his discovery of law of universal gravitation that I remembered from somewhere that I was looking for authoritative reference to cite it properly in my lecture slides, and it's here. So I'll just briefly summarize the first few sections and then read it through the one section where that contains the excerpt that I'm looking for. So in section 7.1, he's talking about planetary motions. He starts out with a summary of what we'll get to in a bit, the Newton's law of universal gravitation. This is the inverse square law statement about the gravitational attraction between everything. Now, there's a story of getting to this law because it's us modern folks. We have the advantage of standing on the shoulders of giants, benefiting from all the work that have been done, all the observations that have been made. So we have the luxury of starting from this law if we wanted to. And in this and the next couple sections is where Feynman tells the story of getting to this law. So we start out with planetary motions. So the first thing that led people to think about what led to the law of gravitation is observing motions of planets among the stars, and trying to come up with a theories that would account for all the features you see in those motions. And he skips through some things. He's skipping through like Galileo and all the stuff. He's beginning with the beginning of modern astronomy, which is the observations of Tycho Brahe, and Kepler is the guy who analyzed Tycho's data, and as he was analyzing it, he was able to derive the he was able to deduce the following laws. These are what we might call a phenomenological law, in that he his starting point was data. So Kepler's first law, we covered this by the way. Kepler's first law says that planetary motion take an elliptical path. And how did he know that? Well, he looked at this data. He first analyzed it under the assumption that it might be a circle, and turned out it didn't really fit if it was a circle. So he started thinking of other shapes that might be similar to circle but still fits, and what the shape that worked out turned out to be ellipse. And Kepler's second law deals with how the speed of the planets vary as they go around in this ellipse. This is the picture that demonstrates it. And the third law, I think there was about a gap of 10 years between his first two laws and the third law. It deals with comparing different planets. He found out the planets that are farther away from the sun move slower. Now, um, so we have these Kepler's three laws of planetary motion, and I call this beginning of modern astronomy because these laws are still today true, with the caveat that it's true to the extent that the sun is the only source of gravity in the solar system, which is, to a largely good approximation. So under that approximation, Kepler's laws are still true. It's not like the Copernican heliocentric model with the perfect circles that we had to get rid of. Kepler's laws are still true with a very specific bit of approximation. Um, but as a law of physics, what it lacks is it's describing a very particular category of object, and um, and physics being fundamental science, we think there's a fundamental law that describes everything. And having a law of planetary motion that somehow doesn't apply to terrestrial objects, that's um, that's not satisfactory. So this is where he takes a little bit of break in 7.3 to talk about Galileo, well, not Galileo, talk about Newton, well, Galileo and Newton. I think the way it's usually taught, at least I teach it out of chronological sequence. So Kepler was a contemporary of Galileo. In fact, when Galileo, there's a letter that Kepler wrote to Galileo as Galileo was writing and advocating for heliocentrism. Tycho Brahe is actually he's not contemporary of Galileo. He comes before Galileo, and so we talk about Galileo more when we talk about like inertia, principle of relativity, and that stuff. Yeah, and then Newton, it comes later after Galileo, after Kepler, and Newton's laws of motion are what we spent quite a bit of time um, working through this semester, and this is what he describes. And this is the section that I want to read in more detail. So, so as we get into this section, what we should have understanding of is the discoveries of Tycho Brahe and Kepler, their 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 description of how the planets move, and development of some basic mechanics, Newton's three laws of motion, describing force, mass, and acceleration. So So this is the culmination of all that understanding and knowledge. So section 7.4. From his better understanding of the theory of motion, Newton appreciated that the sun could be the seat of organizational forces that govern the motion of the planet. Newton proved to himself, and perhaps we shall be able to prove it soon. And by the way, it's quite um, you have to be really good at calculus to be able to prove this. That the very fact that equal areas are swept out in equal times is a precise signpost of the proposition that all deviations are precisely radial. That the law of areas is a direct consequence of the idea that all of the forces are directed exactly toward the sun. Oh wait, so that is actually something that relates to the angular momentum and torque. So maybe that you don't have to be so good at calculus to prove that. Keep going. Next, by analyzing Kepler's third law, it is possible to show that the farther away the planet, the weaker the forces. If two planets at different distances from the sun are compared, the analysis shows that the forces are inversely proportional to the squares of the respective distances. With the combination of the two laws, Newton concluded that there must be a force inversely as the square of the distance, inverse square, directed in a line between the two objects. Being a man of considerable feeling for generalities, Newton supposed, of course, that this relationship applied more generally than just to the sun holding the planet. It was already known, for example, that the planet Jupiter had moons going around it as the moon of Earth goes around the Earth, and Newton felt certain that each planet held its moons with a force. He already knew of the force holding us on the earth, so he proposed that this was a universal force, that everything pulls everything else. This discovery, by the way, was um, by Galileo, and it was one of the discoveries that supported the heliocentric model, and refuted some of the objections to the heliocentric model. The next problem was whether the pull of the Earth on its people was the same as its pull on the moon, i.e., it has, that is, inversely as the square of the distance. If an object on the surface of the Earth falls 16 feet in the first second after it is released from rest, how far does the moon fall in the same time? We might say that the moon does not fall at all, but if there were no force on the moon, it would go in a straight line, whereas it goes in a circle instead. So it really falls in from where it would have been if there were no force at all. We can calculate from the radius of the moon's orbit, which is about 240,000 miles, and how long it takes to go around the Earth, approximately 29 days, how far the moon moves in its orbit in 1 second, and can then calculate how far it falls in 1 second. So this is a footnote describing what falling means. How far the circle of, so if you imagine a straight line path and compare that with a circle, there's a distance there. That's the distance that's being described as falling. This distance turns out to be roughly 1/20th of an inch in a second. That fits very well with the inverse square law because the Earth's radius is 4,000 miles, and if something which is 4,000 miles from the center of the Earth falls 16 feet in a second, something 240,000 miles or 60 times as far away should fall only 3,600th of 16 feet, which also is roughly 1/20th of an inch. Wishing to put this theory of gravitation to a test by similar calculations, Newton made these calculations very carefully and found the discrepancy so large that he regarded the theory as contradicted by facts and did not publish its results. 6 years later, a new measurement of the size of the Earth showed that the astronomers had been using an incorrect distance to the moon. When Newton heard of this, he made a calculation again with the corrected figures and obtained a beautiful agreement. The idea that the moon falls is somewhat confusing because, as you see, it does not come any closer. The idea is sufficiently interesting to merit further explanation. The moon falls in the sense that it falls away from the straight line that it would pursue if there were no forces. Let us take an example on the surface of the Earth. An example released near the Earth's surface will fall 16 feet in the first second. Oh, yeah. So it's this. Let me try doing this. Open image in new tab. Yeah, and let me try having this on the side so that we can read and both see the description of the. Yeah. So in this coming section, he's describing this apparatus. The moon falls in a sense. Okay. An object released near the Earth's surface will fall 16 feet in the first second. An object shot out horizontally will also fall 16 feet. Even though it is moving horizontally, it still falls the same 16 feet in the same time. Figure 7-3 here shows an apparatus that which demonstrates this. On the horizontal track is a ball which is going to be driven for the little distance away. At the same height is a ball which is going to fall vertically. And there's an electrical switch arranged so that at the moment the first ball leaves the track, the second ball is released. That they come to the same depth at the same time is witnessed by the fact that they collide in midair, collide here. An object like a bullet shot horizontally might go a long way in 1 second, perhaps 2,000 feet, but it'll still fall 16 feet if it is aimed horizontally. What happens if we shoot a bullet faster and faster? Do not forget that the Earth's surface is curved. If we shoot it fast enough, then when it falls 16 feet, it may be at just the same height above the ground as it was before. How can that be? It still falls, but the Earth curves away, so it falls around the Earth. The question is, how far does it have to go in 1 second so that the Earth is 16 feet below the horizon? In figure 7-4, I think that's another figure, yeah. We see the Earth with its 4,000-mile radius and the tangential straight line path that the bullet would take if there were no force. Now, if we use one of those wonderful theorems in geometry, which says that our tangent is the mean proportional between the two parts of the diameter cut by an equal chord, we see that the horizontal distance traveled is the mean proportional. I think he means a geometric mean. I think. And by the way, this theorem in geometry, I myself don't remember that geometric theorems are often very useful, and it takes a lot of effort to learn really thoroughly. So I would encourage you to try to make sense of this. Maybe go back and look up your geometry books, see if this theorem was proven. If not, look it up, see where you can find the proof of it. So what I'm saying here is that we see the horizon between mean proportional between the 16 feet fallen and the 8,000 mile diameter of the Earth. The square root of this quantity, which is how you calculate geometric mean, it comes out very close to 5 miles. If the bullet moves at 5 miles a second, it then will continue to fall toward the Earth at the same rate of 16 feet each second, but will never get any closer because the Earth keeps curving away from it. Thus, it was that Mr. Gagarin, Yuri Gagarin, the Russian cosmonaut, was the first person to be on the to achieve orbit, maintained himself in space while going 25,000 miles around the Earth at approximately 5 miles per second. He took a little longer because he was a little higher. Yeah. S is the distance followed in 1 second. I'm pretty. Yeah, I guess that's the ambiguity. So yeah, falling, if you measure it relative to your original orientation, should be perpendicular this way. If you measure relative to where you are, then it should be drawn this way. But so this is the beauty of calculus. This drawing, which would be inaccurate when you're dealing with the large distances. When you're dealing with the very small distances, it becomes approximately correct. So, yeah, and and this is all great. And this paragraph is here is where Feynman demonstrates how we judge scientific theories. So let me continue reading. I'm going to go back to my original view. So any great discovery of a new law is useful only if we can take more out than we put in. Now, Newton used the second and third of Kepler's laws to deduce his law of gravitation. What did he predict? First, his analysis of the moon's motion was a prediction because it connected the falling of objects on the Earth's surface with that of the moon. Second, the question is the orbit an ellipse? We shall see in a later chapter how it is possible to calculate the motion exactly. And this is actually the part where you have to be good at calculus. And indeed, one can prove that it should be an ellipse. So no extra fact is needed to explain Kepler's first law. Thus, Newton made his first powerful prediction, reduced 3 laws of planetary motion down to 2, more or less. The law of gravitation, wait, what is? The professor not giving. There are textbooks, lower division physics textbooks that do go through this. And again, I'll say you have to be really good at calculus to do it. I myself wouldn't try to do it without prior preparation because again, you have to be really good in calculus. And I'm not all that good enough in calculus to do it without prior preparation. Okay, the law of gravitation explains many phenomena not previously understood. For example, the pull of the moon on the Earth caused the tides, hitherto mysterious. The moon pulls the water up under it and makes the tides. People had thought of that before, but they were not as clever as Newton, and so they thought there ought to be only one tide during the day. The reasoning was that the moon pulls the water up under it, making a high tide and a low tide. And since the Earth spins underneath, that makes the tide at one station go up and down every 24 hours. Actually, the tide goes up and down in 12 hours. Another school of thought claimed that the high tide should be on the other side of the Earth because, so they argued, the moon pulls the Earth away from the water. Both of these theories are wrong. It actually works like this. The pull of the moon for the Earth and for the water is balanced at the center. But the water which is closer to the moon is pulled more than the average, and the water which is farther away is pulled less than the average. Furthermore, the water can flow while the more rigid Earth cannot. The true picture is the combination of these two things. What do we mean by balance? What balances? If the moon pulls the whole Earth toward it, why doesn't the Earth fall right up to the moon, collide with it? Because the Earth does the same trick as the moon. It goes in a circle around a point, which is inside the Earth but not at its center. The moon does not just go around the Earth. The Earth and the moon both go around the central position, each falling toward this common position as shown in this figure. This is the common point, very center or center of mass or center of weight of Earth and moon. The motion around the common center is what balances the fall of each. So the Earth is not going in a straight line either. It travels in a circle or ellipse, which is quite close to circle. The water on the far side is unbalanced because the moon's attraction there is weaker than it is at the center of the Earth. where it just balances the centrifugal force. The result of this imbalance is that the water rises up away from the center of the Earth. On the near side, the attraction from the moon is stronger, and the imbalance is in the opposite direction in space, but again, away from the center of the Earth. The net result is that we get two tidal bulges. So, yeah, I think this is the section I want you to read through in detail, mostly for this description here of Newton's discovery and testing of the inverse square law of gravitation. The, this is a description of science as it ought to be. You know, we make a prediction and we test that prediction against experiment, against known facts, experiment data. I guess Newton didn't really do any experiment of his own. He was relying on measurements made by others. And, you know, when they disagree, then we we fix it, or we maybe we learn from that disagreement. So here, I guess what Newton learned was, well, he found the discrepancy, and he thought the theory wasn't correct because, you know, it was contradicted by existing fact. But, you know, he didn't just forget about it, get rid of it entirely. And when he learned of an update that might change the prediction, he redid the calculation, and once we had agreement, then he published, and all that. That's a kind of an example of how science ought to work. We make predictions, and we test it, and you know what to do when the predictions don't agree with the experimental results don't agree with the prediction. That's a whole topic on its own. I think there are scientists who think, especially in other fields, who think that we call it publication bias, in the sense that we scientists tend to want to, and the peer-reviewed journals tend to want to publish only the results that show positive result. Kind of equivalent to Newton not publishing his result because he saw a discrepancy that he considered to be too large. And what if no one never ever made a new measurement of distance to the moon within Newton's lifetime? Then what would happen? So in the scientific world, there's a bias for publishing and making others aware of the positive result, as in results that seem to show something new. When someone did an investigation and it's a negative result, as in the result didn't show anything apart from what someone would just guess offhand, then because it's not considered novel, people don't publish it, and you know there's a reason for that. But sometimes that kind of publication bias can lead to systematic bias in a field that's not healthy for the field. So that's a whole another topic, but I'll leave that for you. But I guess what I can ask, if you're interested in the topic, what you can do for yourself is search up something called the replication crisis, because it has to do with crisis to a degree of where there are some scientific results that don't appear to be replicable. It's not something that affects physics all that much, but it's it affects how we. It's an epistemological. It's a problem of knowledge gathering because we rely on this scientific process, and there seem to be results that we thought were reliable, but are not apparently. So I'll leave that there. It's not really a physics topic. So I was thinking through what I could do today, and I think this is something that I've done for my astronomy class. but I think it might be worthwhile to do here. So this is it's just a link to a website for the software. It's technically a game. There is a free version that's I think available here. I'm going to use the one that I bought on Steam. It's a well, I guess they're calling it Universe Simulator. It's a really a good software for illustrating some of the things in astronomy. You do have to be careful to, especially when you're using for real world demonstration. You have to turn off what's called a procedural object. But so I just want you to just to play with it and kind of talk over some things. So yeah. So let me do that. I'm let me do it this way. So let me run the space engine, and I think I have to change my share setting. I have this vague recollection of doing the normal Zoom share setting with the SpaceEngine before, and doesn't quite come through right. So my experience running this software in the in previous classes was with the Zoom's regular share setting. I think this comes it's trying to send it through too high resolution. So I'm going to just change my share setting so that it's optimized for video clip. I'll see how well that goes. Um, so this is a quite demanding software. It actually um, it uses a fair amount of computing power, both in terms of the CPU and GPU. And I have a laptop that I got this past May that's more powerful than any of the computers I've had before. Then running this software wouldn't really have been possible and have a smooth-ish Zoom experience. So, anyways, so I changed the settings. Hopefully, it'll turn out a little bit better. So this is planetarium software. Let me just do a couple of things here. I'm gonna turn off the orbit because that's it's useful for some things, but I'll do that later. Let me see here. Let me go to the more familiar view first, planet Earth, and and as I was saying, it's technically a game. You can I guess it's a kind of odd kind of game, even odder than Minecraft, because even in Minecraft you can, affect the world you are in. This is a more of a spectator kind of game, so you can look at the things. Let's see, are we on real time now? No, that's not real time. Let me try to change to yeah. So this is real time. This is right now, today, and let me see. I feel like I'm upside down on this. Let me just because that's South Pole and that's on the top side here. So there's a bit of control that I want explain over explain. So I'm using mouse for control, and depending on whether I'm clicking the left button or right button, the how the camera view changes shifts, and there's a whole shortcut of things that I try to remember. If I forget and I need to look it up, I'll come back here and look it up. Um, so what I want to start out with, can I just close this? With this, so that object there, it used to be called, I think, Andromeda Nebula, because it looks like a nebulous kind of lens-shaped thing. It stands out by its size because it doesn't look like a point of light, and it's not the sun, it's not the moon. It's in terms of angular size, it's bigger than the planet. And let me zoom in like zooming in with a telescope. So when you as the people were actually observing Andromeda Galaxy, what we now know as Andromeda Galaxy with the telescope, they saw these features. And I think it's accurate distance measurement to Andromeda Galaxy that established it as being something that must be outside of Milky Way galaxy, our own galaxy. That's relatively recent. I think that happened somewhere in the 20th century, early 20th century. So, well, this is a view of Andromeda Galaxy. Now, so all of this is an interesting thing to look at in an astronomy class, and I do now in a physics class. I guess other than just appreciation for the natural world, or the physics, the natural world we live in, it might not look like a terribly relevant to physics. So let me show something that has a more direct connection to what we've been covering. So one of the things I was thinking through, and that's why I thought demonstration of this software would be good, is the discussion of the gravitational interaction with the celestial bodies. um, there was a in the section of the Feynman lectures that I was reading through on Monday. There's the one that talks about Earth falling towards the moon or something along that line, and you can see those orbital mechanics in this software. So I'm going to turn on the orbits of the things because that helps me orient myself and look for the features of the things that I think would be interesting. Let me make sure I'm on the correct side of the hemisphere. Just for consistency's sake, I want to be, yeah, okay, I want to turn this around. Because most of the orbital pictures that's shown will normally place you so that north is up. That's what I'm trying to do. So that's the south, that's the Antarctica, so that's down. And this is the north, which is up. Okay, good. So so you see several lines drawn here. Let me zoom out or move away from the Earth so that I can show some of these better. So right now I have Earth selected, and Earth is going in kind of two different kind of orbit. So there's a larger orbit of Earth around the Sun, and that orbit is represented by this line here. So to show that, I had to zoom way out. When I zoom way out with the sun in view, you can see this is the orbit of the Earth and Moon system around the sun. Let me go back to. So what these orbits are describing is orbit of the Earth-Moon system around each other. So that's moon. When I click it instead of moon, it'll actually select one of the Apollo spacecraft that's landed on the moon. Let me use the search feature to select the moon. So that's the moon. It looks like it's orbiting Earth, and that's the description we can give of Earth as being, moon as being gravitationally bound to Earth. And this orbital motion of moon is moon falling towards Earth, in that if there was no gravity of Earth, it would be going in a straight line. So compared to that straight line, it's falling away from that straight line into this circular-ish orbit. Now, I said I would demonstrate what Feynman was talking about, Earth falling towards the moon. So when you look here, Earth is not stationary. In the kind of Earth-Moon system, Earth itself is actually also orbiting. It's orbiting in this small circle here. And the kind of the central point that Earth is orbiting around, and Moon is orbiting around actually as well, is this point here. This is what the program is calling planetary barycenter, or center of mass. This point is the center of mass of Earth and Moon. So Earth is, massive enough that this center of mass of the Earth-Moon system, it lies inside the Earth. You can see as I change my observation point around, it's just inside the Earth. But Moon is also heavy enough. Moon is actually quite unusual amongst natural satellites in just how large it is. compared to the major planet that is orbiting, that this center of mass is noticeably not at the center of Earth. It's this offset quite a bit, and Earth is orbiting around this point. That's what this green orbit is showing. So yeah, that's that's what Feynman was talking about. Earth, just as the moon is falling towards this point, center of mass, and Earth is also falling towards this point. So that's the Earth-Moon orbital mechanics. And I can show you the kind of orbital mechanics of the solar system. So let me actually do this. I'm gonna go to sun so that the sun is kind of centered. Okay, so this is kind of the view that's difficult to obtain in real life, because in order to have this view of the sun and the planets orbiting around the counterclockwise, you have to be basically above what I would call what's called ecliptic plane. That's the plane of the solar system. We do have some spacecraft that has gone out of this plane of the solar system, and but it's like one of the Voyager spacecrafts have gone in that direction, but that journey takes a very long time and has to travel through quite a bit of void, because most of all of the major planets in the solar system is in this very thin plane, and this actually comes from physics. So these bright green lines, they are all orbits of major planets. So if I go in this view, you can kind of see it. So in the very outermost, this should be, guessing, I think it's a Neptune. Is it Neptune? Let me try to click it. Yeah, it's Neptune. So Neptune, Uranus, Uranus, Saturn, Saturn, and this is Jupiter. By the way, I'm starting with those outer planets to show the scale. This is how far away those outer planets are. And Jupiter, it's the distance is being. Oh wait, that's distance from me, not sun. So that might not mean anything. So that's a Jupiter, and all the inner four planets, they're in this tiny circle here. So if I want you to actually see where they are, I really need to zoom in so that you can distinguish them. This is Mercury. Sorry, those asteroids are really in the way. That's Mercury, the closest the planet. That's well, that was Earth. Uh, that's Venus, and this is Earth, and that's Mars. And when we talked about Kepler's laws, I in the lecture I did talk a little bit about how Kepler, there was some element of fortune in that Kepler was analyzing motion of Mars, because when you look at orbit of planets like Venus, this is really close to circular orbit. So if Kepler was analyzing orbit of Venus, or the by analyzing orbit of Venus, he might have concluded, yes, planets do go around the sun in a perfect circle, and that wouldn't have led to the discovery that he did make. And I think Mercury does have a quite elliptical orbit, but Mercury is harder to observe from Earth because it's closer to the sun. So there's many parts of its orbit where it's simply not possible to observe it from the Earth unless you go outside the atmosphere so that you can just see it anytime. And so this is the orbit of Mars, and imagine it with the sun at the center. I think I'm more or less directly above it, so that if its orbit is perfectly circled, then this should look perfectly circular. Just notice how close to a circle it is. It is elliptical in that I think the center should be somewhere around here, but the sun is not at the center. It's at one of the two foci or focuses of the ellipse. And this is how how remarkable the level of precision in the data, in Tycho Brahe's data that you need for Kepler to be able to figure out the orbit of the Mars doesn't exactly fit a circle, but it's quite close. So, and that's why that's the beginning of modern astronomy, one that's centered around collection of accurate, reliable data, instead of philosophizing about how the heavenly bodies should move and whatnot. So the reason we have this ecliptic plane, the plane where things, most big things are in, is because of conservation of angular momentum. If you think about life cycle of a solar system like ours, you can imagine kind of stellar nursery, a cloud that's eventually going to collapse. The vast majority of the mass will form this star, and the rest of the stuff will be hanging around as the planets. And when you have a collection of gas, I think it's not too unlikely to imagine that the collection of the gas might be rotating in some direction. It would take quite a bit of coincidence for that gas to be perfectly kind of not have a net angular momentum. It just it'll have some random value of angular momentum. And the thing about the gravitational interaction is that it's a central force. It's a force that acts along a straight line between the two objects, and with under influence of central force like a gravity, angular momentum is conserved. So as the cloud of gas collapses and becomes the solar system, it has to conserve angular momentum. And what that means, if a mass that's farther away is moving in, if it was orbiting very slowly, it has to now orbit, it has to move faster in order to conserve angular momentum. And as it moves faster and faster, at some point there's a kind of a balance between centrifugal force and the force of gravity pulling it in. So if you imagine angular momentum pointing one way as that cross product vector quantity, in the plane that's perpendicular to that angular momentum, there will be some limit to how close the material can come in. At some point, their orbital speeds will be enough to keep them in a stable orbit like this. But in the direction perpendicular to that plane, that's where things can collapse all the way down, and that's where you see this plane. So the net angular momentum of the solar system is in the direction perpendicular to this plane. And that's also the reason why when you look at the solar system, there's a kind of natural direction that everything is rotating in. That's the that's the direction that corresponds to the net angular momentum of the solar system. So you could imagine in the early stages, there might have been some pieces flying around. In fact, we still have some pieces flying around in the asteroid belt. There's quite a few asteroids here, and just trying to click to the biggest one, Eris. Ceres. That's the biggest asteroid. It's the only one in the belt big enough to be classified as dwarf planet. So there might be some, tiny pieces here and there that's going in the wrong direction. That's orbiting clockwise from this view rather than counterclockwise. But if you imagine solar system existing over geological timescale, billions of years, when there are objects just flying in, going the wrong way, at some point it's going to hit something else. And over those millions, billions of years, with the things colliding, everything will, the things that achieve kind of stable arrangement will be the things that are going in the roughly the same direction. Um, so yeah, in this view, so I can also speed up the time to show some of the things that we talked about. We talked about Kepler's law. So in the picture of the orbital path, you've seen illustration of, I guess, Kepler's first law, that the sun is at the center of the ellipse or elliptical orbit. I can demonstrate. Can I? Um, Kepler's second law doesn't like hit you like a brick as much as Kepler's third law. So I'm gonna speed this up quite a bit so that orbit of Mercury will be relatively fast. I think I need to speed it up a little bit more. So, okay. At this time scale, about 1 second in the simulation is 1 day, 1 Earth day. So you can see how quickly Mercury is moving, not that fast. Let me speed it up a little bit more so that it looks like Mercury is whizzing by. Okay, so in this time scale where every second is about half a month, maybe, you can see how quickly Mercury is orbiting, how quickly Venus is orbiting, how quickly Earth is orbiting, how quickly Mars is orbiting, and how quickly Jupiter is orbiting. And I hope you can see that these inner planets are moving faster. It's not just that they completely orbit more quickly, it's that they are also moving faster. Their actual speed is faster. So these outer planets, they have a long orbital periods. Like even Jupiter, the innermost of the outer planets, take 11, 12 years to complete one orbit around the sun. And yeah, so that's a kind of the view. And so compared to Saturn and Uranus, the Jupiter now looks pretty fast compared to Saturn and Uranus, which are slower than Jupiter. And so yeah, that's Neptune, outermost major planet. And way back in, when was it, 2006, 2007, that's when this redefinition of planets happened. So before then, they didn't really distinguish between major planets and minor planets or dwarf planets. Things were just a planet or not a planet. So during that time, one of the objects that used to be classified as planet was Pluto. And I think I can identify Pluto if in this picture with the orbital orbits marked. I think I can identify just from the features because there are some things that are just odd, weird about Pluto. So I think it's easier to see if I go out of this plane. So look at the plane from the side view. So with the major planets, as I was saying, their orbits are in this tight range of ecliptic plane. One of the things that looks off about Pluto is that orbital Pluto is not in the ecliptic plane. It's at a bit of an extreme angle. And I think which one would it be? Want to guess that this is Pluto. Let me see. Yeah, that is very center of Pluto, Charon. Charon is pretty big compared to Pluto. So it's the moon of Pluto. They are both double tidally locked. So look at the orbit of Pluto, compare it to orbit of the major planet. That's kind of the first thing that, as people were learning more about the properties of Pluto, that as they made long enough observation to project its orbit, which actually takes quite a bit of time, 250 years, that it doesn't fit the same pattern that major planets have. And that's because it's kind of a different material, I guess. So these objects that you see with the orbits projected out, these are the confirmed dwarf planets I guess that they are called the trans-Neptunian object, TNO. Their orbits are mostly beyond the orbit of Neptune. So Makemake, is this Eris? I'm looking for. There should be Eris. Oh, I see. Eris is this one. So Eris, who's discover? It's one of the first dwarf planets because it's the discovery of Eris that really put status of Pluto as planet kind of in danger because there are ways in which Eris is very similar to Pluto. So look at the mass of Eris. That's about 23% of the mass of Moon. And when you look at the mass of Pluto, if I can select the Pluto,
All right, I'm just going to use the search feature. So many. So mass of the Pluto is actually less than mass of Eris, 18% of mass of Moon. So these two objects are similar in size. Um, and they kind of share similar-ish orbit. Eris is maybe a little bit farther out than Pluto is, and they are actually their orbits are so elliptical that there's portions of their orbit where Eris is actually inside the orbit of Pluto. But the point is that they are both of similar size, so it's kind of nonsensical for us to say, oh, Pluto is a planet because we found it earlier, and Eris is not a planet because we found it later. That's just so arbitrary, and we scientists try not to be arbitrary, although often we end up being arbitrary, but we try not to be. So there were the International Astronomical Union, they were trying to develop some kind of consistent definition. And one criteria that they settled on is the criterion of what's called clearing the neighborhood around its orbit. And really, that's the thing that you can, kind of a concrete thing you can look at between the major planets and these many trans-Neptunian objects that are kind of like a planet. They are bigger than asteroids, but we kind of want to avoid defining them as planets because there are just so many of them. It was nice when we had 9 planets with Pluto. 9 is a nice number. But if we start making Pluto and Eris planet, and we would have to make these planets, then we would end up with 20 or so planets. And it's so unwieldy, like the label of planet wouldn't mean anything. So the distinction that they settled on was how the orbital features. So as you look at here, you can see with the orbits of the major planets that they are the dominant body within their orbit. There's no other body of a similar size that's occupying the same orbit, and that's kind of a factor of gravity. These major planets are large objects in their orbit. They influence all the other things around their orbit. So either things that are near them either get captured as a moon, or they get accreted into the planet itself, or they get knocked out of the orbit entirely. So so all these bright green orbits of the major planets, they show neighborhoods that's been cleaned out by the planet, the major planet. These minor planets, they are the kind of, they are big enough in their own orbits, but as you look at it, there's quite a bit of overlap between orbits of these different bodies of Pluto and Eris and all these other minor dwarf planets. So they haven't cleared their neighborhood. They are not big enough to push away or somehow gravitationally dominate other objects that are in a similar orbit. So based on the criteria, these trans-Neptunian objects, which are also outside of the ecliptic plane, they are not major planets. So let me show one of the comets. The most famous comet that you might have heard of is Halley's Comet. So that's this is another astronomical object whose discovery is prehistoric, as in even in the earliest written material, you can find references to a celestial object that, with our better knowledge of astronomy, we can identify this. Oh, that is Halley's Comet. So if Edmund Halley wasn't the person who discovered it, why is it named after him? It's named after him because he's the one who recognized the periodicity of Halley's Comet, that it's a celestial object that becomes visible in our sky once every 75 years.
And that's suspiciously similar to typical human lifetime. So this is the kind of comet that everyone says maybe once in their lifetime. So appearance of Halley's comet is associated with superstition like end of world, because it's a kind of once in a century thing. Every time it appears, people alive then have never seen it before. It's sign of times, world is ending. And Haley recognized this kind of sighting. It's occurring on some regular-ish interval, and I think Haley's he's around after Newton's synthesis of his theory of gravity and derivation of Kepler's laws based on the mechanics, uh, and he, I think, I don't know. I'm terrible storyteller. I'm terrible historian. I'm even worse a storyteller. But I imagine Haley looked at the records of sighting of the comet and recognize that there's a periodicity. So it becomes visible to us when it comes near the kind of near the sun in the inner part of the solar system. And when astronomers describe a very long period object, they, forgetting the name of the process they go through, they can often, with that benefit of identification of the object, they can go back to the historical astronomical records that go back to the kind of the Middle Ages, the Islamic scholars, ancient Chinese records, and with the knowledge of what it is they are looking for, they can identify, oh, this record is referring to actually this Halley's comet. And they do that with the Halley's comet and with the other objects as well. So, like, Pluto, it has period of 250 years, and that kind of measurement can be made more precise by looking retroactively at previous records that didn't fully recognize what that object is. So let me do this. I think I can use Halley's comet to illustrate Kepler's second law. So you can see with this orbit here, I'm trying to move it around so that you can get a better view of the three-dimensional arrangement of the Halley's comet's orbit around the sun. So it is outside of the ecliptic plane. It's at this angle, and it's a hugely elliptical. So so the focuses of the ellipse that this elliptical orbit is at. So one of them is at the sun, Kepler's first law, and the other one is over here. So it's elliptical to a degree that none of the planets or dwarf planets are. So let's see, what view is the. I think this is decent enough view to kind of see the orbit of Halley's comet. I'm going to reset the time to our current time. So Halley's comet last appeared in the 80s. So right now it's very far from the sun. It's like a halfway point between its two sightings. So so where it is now, you can't. We can calculate where it should be, but the core of the comet is so small that even with the most powerful telescope, we shouldn't be able to see. But that's where it should be based on its known orbital characteristics. So I'm gonna speed up the simulation time a little bit so that the motion of Halley's comet in this outer edge is still visible, because it's going to take it another 30 years or so to come near the sun. So let me speed up the simulation time enough that it looks like it's moving. Okay, maybe that's enough. So I can see that a little dot that's moving there, and it's moving slowly. And as the simulation is fast enough that every second right now is about a year. And I want you to, and I'm just gonna leave the simulation speed alone so that you can make a proper comparison. See how quickly or slowly Halley's comet is moving. So this so Kepler's second law says that the areas, oh sorry, let me just pause it briefly. The area swept out by the line connecting the planetary planet, in this case it's comet, but Kepler's second law applies to comets as well. The area swept by a line connecting this object to the sun, area swept by that line in some amount of time, is equal for all the points in the orbit. So out here, that line was longer. So as it moves slowly, the kind of the pizza slice that it's sweeping is fairly sizable. Now, as it's moving in, the line gets shorter. So in order for that line to sweep the same area, the comet will have to move faster and faster. And I'm going to resume the simulation and watch how it gets faster as it gets closer to the sun. So near the perihelion, it goes by super fast. So the entire orbit of Halley's Comet again is 75 years. This I'm gonna just reverse the time a little bit so that we can look at that close approach a little bit in more detail. Okay, I'm just reversing the time a little. Okay, good. Gonna reverse it again, and oh wait, I can't reverse the while it's paused. Okay, and I'm gonna just zoom in a little bit so that we can look at the perihelion of the Halley's Comet with a little bit more. Okay, and I'm gonna slow it down so that it doesn't go by so quickly. Okay, so as it's entering kind of the range of the asteroid belt where Ceres is, so that is around, or that is going to be around the 2061, beginning of that year. Okay, and I don't know if the comet would be visible at that distance. So what makes a comet visible is, let me zoom in with a telescope to see if it might be visible. No, I don't think it would be. So yeah. So the comet doesn't really become visible until it develops that. Oh wait, it is developing the tail. Okay. So I'm gonna zoom in a little bit more. So you can see that. So the comet's core is a really tiny ice, a dirty ice ball. That's the description of comet. And when it's way out, far away from the sun, that tiny ice core, it's basically not visible. It's a yeah. It does it. Yeah, the diameter is 11 kilometers. It's like size of a city, super far away. Can't see it even with the most powerful telescope. The part of the comet that becomes visible to us is this tail. And let me track the comet so that the camera will just follow it as it gets near the sun and then moves away. So around the beginning of 2061, that's when, with a really powerful telescope, you might be able to begin to see the comet. And start the simulation again. Maybe a little bit slower. Okay, faster. Okay, I'm gonna zoom out a little bit because I can't tell where the comet is in its orbit. It is okay. Okay, it's still beyond the orbit of Mars. Let me just track it until when it's inside the orbit of Mars. So somewhere here. Okay. So at this point, the comet would be somewhere at a similar distance as how far away Mars is from us. And okay, that doesn't seem to have changed all that much. So I'll move the simulation along until it's inside the orbit of Earth. And I think by this point, the tail should be much more visible. Yeah. So the sunlight is heating up the ice ball, and it's evaporating of stuff from the comet. That stuff is getting pushed out by the solar pressure, radiation pressure from the light from the sun. and that's forming this tail. And the tail of the comet, it's not tracing the path of the comet. It points away from the sun, and it's beginning to develop the two tail. I think the more volatile material points more directly away from the sun. This is the heavier dust. And see here, I'm gonna zoom out. And I think by this point is where the comet would be visible to naked eye observer without any telescope. And it's also near Earth, that helps too. And as it gets, so this is the perihelion at the closest point to the sun. That's where the tail would be the brightest and biggest, and that's the so the comet was in the view at the beginning of the year 2061, and around the end of May, June, that's when it's at perihelion, when it's the brightest. It's scaring the most number of people, at least before we knew what it was. And it's gonna take another few months to move out of the range and become invisible again. So it's moving out of the range of the orbit of Mars around here. So the comet would have been visible in the night sky for maybe a few months. So yeah, that's a kind of orbital mechanic illustration that I can show with this simulation. Yeah. Am I okay? Yeah, and there are other things I can do, but I see that I'm over time, so I think I'm gonna end it here. There are, I guess, there's a lot of fun things in the